So let me quickly show you how to do that. I'm going to share my screen right now. Okay, I hope you all can see my screen.
Yeah.
Okay, so I'm just going to quickly show how to execute partition finder. Okay. So what I do is I go to the command prompt, right, and type CMD and get the command prompt. It looks like some of you don't know the difference between the command prompt and a Python prompt, right? So I open my command prompt, type Python, right, and I don't press enter. The moment I press enter, Python is going to expect like Python commands, right? And we are not going to give it Python commands right now. So Python followed by a space, and then I have to input the partition finder program to Python. Okay. So what I do is, if you can see my screen, I just drag the partition finder application to my command prompt screen and paste it there. There you go, right? And then followed by another space. The only parameter that partition finder takes is the folder in which your config file and your fileup file are, right? So that is this present folder that I have that you can see in my screen. So you can see that there is a config file over here, and there's also a fileup file, primates fileup file over here, of which I want to find the models for, right? So I just go one step back to the previous folder and drag and drop this folder as one of the as the only parameter that partition finder takes. Now, if I press enter, partition finder will start running, right? It's just as simple as that.
Chaitanya, which version of Python are you using? 2.7.5?
I think so, yeah, 2.7.5.
Okay.
So does that answer your question, Prashant?
Yes.
Okay, cool. And Akshop, you had a question.
Yeah, so my problem is a little different. I know how to run it, but since I'm on a Mac, I am not able to delete 3.7.3, and thus it doesn't just run it. It just gives me an error. I don't know how to go about it.
Okay, so have you gone through the manual for partition finder? Because there is a different way to run partition finder on Mac.
I have not been able to. I've been searching it since 2 days, but I've not been able to find how to run it.
No. So just go through the manual. So in the partition finder folder, there should be a folder called doc. Maple, can you just put that folder on?
So you see this folder called docs, right? So open that, and you see a manual over here. So you can go through this manual and
you're running partition finder.
Installing Python on Macs, right?
Okay, I'll do that.
Yeah. So guys, see, the bottom line here is that you guys have all you need already. It's all there in the worksheets that we have shared and or the document manuals, right? If you don't find it there, it's probably explained in the videos that have been shared. All you need to do is look, okay? And despite all of this, if you can't figure it out, then we'll help you. Yeah. Okay, I think we should move on to today's presentation. So we're going to talk about Bayesian inference today. So we use Bayesian inference also to build trees, just like what we do with maximum likelihood. There are, in fact, it's interestingly, Bayesian inference uses likelihood to to get to the most probable trees and so on. But it does a few other things as well, apart from what RAXML would do. So we'll talk through all of that, and you guys can, as usual, stop me in case you have questions, and we'll take it from there. Yeah, but you need to pay a little bit of attention with this presentation, because if you miss the first few slides, then it gets a little difficult to follow. All right. So I'm jumping straight into the presentation, and this is something that I've shared with you guys this afternoon. Sorry about that. Okay.
Maybe can you just put that thing on hide?
Yeah, I will. Okay. So can you guys see my pointer? It's really tiny. I'm moving it around.
Yeah, but it's barely visible.
Yeah, it's a little red. So should I just go back to my usual mouse pointer?
I think you can increase the diameter.
No,
but
I really tried this afternoon. I couldn't.
Okay, no, that's fine. That's fine.
So is this fine? Is this
That's
better?
Fine. This is fine.
Cool. So let's stick with the mouse pointer. Cool. So let's go with Bayesian approach. And so just to jog your memory, so because for you to understand Bayesian, you have to kind of remember what likelihood is, because Bayesian uses likelihood in the end, right? So the first two slides will probably jog you through that. Let's move on. So in any situation, for the kind of work that we do, we'll be collecting data from the field, and that would be our data set, right? In our case, this data D1 you see over here is basically a sequence alignment, right? And what we're essentially doing with likelihood and the Bayesian approach is we are trying to test which tree suits the data the best, right? So each tree therefore becomes a hypothesis. So in a sense, maximum likelihood and Bayesian, they're doing hypothesis testing to give you the right or give you the most probable tree for your data. Okay. Now, if you remember from Roy's session yesterday, he was telling us that likelihood by definition is the probability of the data given a hypothesis, right? And what is our hypothesis here? It's basically a tree, right? So what we're essentially doing with likelihood is we're trying to find out the probability of the data that we have given a certain hypothesis or a certain tree, right? Now this becomes the likelihood of tree 1, okay? Similarly, we calculate the probability of getting this data given tree 2, and then tree 3, tree 4, until all the n trees are exhausted. The n possible trees that we have for this given data. However, programs like RAXML would not evaluate all possible trees because it's a heuristic method and not an exhaustive method. Same thing with a program like MrBayes, which does Bayesian Inference. It's not going to evaluate all possible trees. It's going to use heuristics to try and get to the right tree. Okay. So likelihood, therefore, is probability of the data given the hypothesis, or probability of t given h, as you see here. That's how it's represented mathematically. Okay. On the other hand, if you look at the Bayesian approach, what we're trying to do is, given the data, right, we are trying to find out the probability that tree 1 is correct. Okay. And then we find out the probability that tree 2 is correct, right? And then tree 3 and so on till we exhaust all the possible trees for this data. Okay. So the fundamental difference between this approach and likelihood is that likelihood tries to calculate the probability of the data given the hypothesis, whereas the Bayesian approach calculates what is called posterior probability. Okay. And posterior probability is probability of the hypothesis given the data. And it is represented like this mathematically. I can't find my pointer. Oh, there it is. So this is how it is represented mathematically. Probability of the hypothesis given the data. So in essence, the difference between the two approaches is where you actually put the probability function. Yeah. Okay. Now. Yeah.
What I understood from you right now, this is getting a little bit hard for me. So in Bayesian approach, we have the data as the first subject, and based on data, we are having the tree as the hypothesis.
Correct.
Data is the priority.
Correct.
And
no, it's not about priority at all. It's about where you put the probability. So if you can see my mouse pointer here, right? You see my mouse pointer, right? So this basically says that this means probability of the hypothesis given the data.
Okay.
Right?
And what would be this in maximum likelihood?
So if you, I'm just going back to the previous slide. So in maximum likelihood, it's probability of the data given the hypothesis.
Okay. Okay.
So likelihood basically assumes that for tree 1, it assumes tree 1 is the right hypothesis, right? And it tries to calculate the probability of getting the data that you have given tree 1. Okay. Similarly, probability of getting the data given tree 2, right? So that is the very definition of likelihood. Okay, got it?
Yes, got it.
All right. All right. So these are the two parameters that we're going to be dealing with today: likelihood and posterior probability. So, like Roy was mentioning yesterday, that these heuristic algorithms, right, or heuristic tree building methods, like you can have, like, say, for example, parsimony or maximum likelihood and Bayesian too. So all these methods optimize for a certain criteria, right? So what does parsimony optimize for?
Number of steps.
Yes, the least number of changes, right? Similarly, what does maximum likelihood optimize for? It optimizes for the likelihood, right? And the tree that gives you the most likelihood or the maximum likelihood is probably the tree that best explains evolutionary relationships between the organisms that you have in your hand. On the same lines, the Bayesian method tries to optimize for posterior probability, right? So according to the Bayesian method, the tree that gives me the highest posterior probability is the tree that best explains my data. Yeah. So let me move on to the next slide. Okay. Don't get freaked out by that equation on top. We'll just break it down and then you'll understand it very clearly, though it looks a little intimidating.
Chaitanya.
Yeah.
So in some sense, does posterior probability and bootstrap are similar?
Actually, in the sense of calculating the final posterior probability for the tree that you want using MrBayes, it is in a sense similar to bootstrapping. But the methods are completely different, right?
Okay. Okay.
Just the way the numbers are arrived at. For example, when you say a bootstrap value of 98, right, and a posterior probability value of 0.98 for the tree, right?
Right.
For the whole tree I'm talking about. In a sense, the way these numbers are arrived at is the same, right?
Oh, great.
But
Yeah.
bootstrap is for a completely different purpose, and posterior probability is for a different purpose.
Okay. Okay.
Right. Okay, so let's just quickly look at this equation. So here on the left hand side, you see that the left hand side is basically probability of the hypothesis given the data, correct? And that's nothing but your posterior probability. We just saw that in the previous slide. So the formula for calculating posterior probability is, in the numerator, you have the probability of hypothesis 1, okay, multiplied by the probability of data given the hypothesis, right? So can anyone unmute and tell me what probability of data given the hypothesis is in English?
Is it the likelihood?
It is the likelihood. So in the numerator, you're basically dealing with the probability of hypothesis 1 multiplied by the likelihood of hypothesis 1. All right. And in the denominator, you have the same as the numerator. So probability of hypothesis 1 multiplied by the likelihood of hypothesis 1 plus probability of hypothesis 2 multiplied by likelihood of hypothesis 2. Now, this equation assumes that there are only two possible hypotheses for this particular situation that we're going to deal with. Okay. If there are let's say 10 hypotheses, you will have to extend this denominator to up to 10. Okay, because here we have only two hypotheses. We just say probability of hypothesis 1 multiplied by likelihood plus probability of hypothesis 2 multiplied by likelihood of hypothesis 2. Right. This is the Bayesian equation, and it is an equation that is widely used not just for tree building but for various in various other fields. Right. So it basically gives you the posterior probability of the occurrence of an event given a set of events and so on. So it can be used in any context. It's a very useful equation to learn, and a lot of people who have done statistics courses would have. You cannot escape the Bayesian formula, right? Okay. Now, to understand the import of the Bayesian thought, right? So let's take an example, and which might kind of explain this a little better for you guys. So let's assume we have two bowls, okay? Bowl 1 and bowl 2, and in bowl 1, we have 10 chocolate cookies and 30 plain cookies, and in bowl 2, we have 20 chocolate cookies and 20 plain cookies. Okay. So here's a question. So when someone randomly picks a cookie, let's say this person is blindfolded, he can't see, and he randomly picks a cookie and it turns out to be a plain cookie. Okay. Now, what is the probability that this plain cookie was picked from bowl 1? Okay. So it is this kind of questions or problems that the Bayesian formula helps solve. Okay. So the way I would interpret this is, let's say bowl 1 is my first hypothesis and bowl 2 is my second hypothesis. So in a sense, this guy has a plain cookie in his hand. There are possibly two bowls the plain cookie could have come from, right? So my first hypothesis would be that I picked the plain cookie from bowl 1. My second hypothesis is I picked the plain cookie from bowl 2. Simple enough. And my data here is a plain cookie. Okay, D over here is the plain cookie, right? Now, what is the probability that I picked the plain cookie from bowl 1? Given that there are only two bowls, the probability that I picked the plain cookie from bowl 1 is 0.5. I hope everyone agrees with that. Now, what is the likelihood that the plain cookie came from? What is the likelihood of getting the plain cookie from bowl 1? Right. So I put my hand in bowl 1 and I pick a cookie. What is the likelihood that that will be a plain cookie? So that basically is probability of data given the hypothesis, which here is basically 30, because there are 30 plain cookies in bowl 1 divided by 40. This is the total number of plain cookies, right? A very simple like a probability thing, right? So 30 by 40 is 0.75. Similarly, the probability that I've picked the plain cookie from bowl 2 is 0.5, and the likelihood that I picked the plain cookie from bowl 2, right, or the likelihood of picking a plain cookie from bowl 2 is 0.5, right, because there are totally 40 cookies and out of which 20 are plain. So I just apply whatever we have here to the Bayesian equation over here. Okay. So, and I just substitute the values that I have for my problem into the Bayesian equation, and I get a value of 0.6. It's 0.5 multiplied by 0.75 divided by 0.5 multiplied by 0.75 plus 0.5 multiplied by 0.5. I hope everyone is clear and with me so far. So here, 0.6 is basically my posterior probability. Okay. So in essence, what I'm saying is, if I'm blindfolded and I pick a cookie and it turns out to be a plain cookie, the posterior probability of the plain cookie coming from bowl 1 is 0.6, right? Okay. However, let's assume we did none of this gymnastics right now, right? Let's say there are 2 bowls and you're still blindfolded. You pick a cookie, okay, and it turns out to be a plain cookie, and someone asks you what is the probability it came from bowl 1, right? Intuitively we'd say 0.5, right? Because there are only 2 bowls, right? So that basically, when you blurt out saying that, okay, there's a 0.5 chance or a 50% chance I picked it from bowl 1, you're blurting out what's called prior probability, okay? But posterior probability, as you can see, is a slightly more informed probability of the occurrence of a certain event, right? And that is why the Bayesian inference uses posterior probability to do a whole bunch of things, okay? So here, as you see, the probability of the cookie coming from H1 or 0.5 is the prior probability of picking the cookie from H1, right? The probability of picking the cookie, probability of picking the cookie from H1, given that it's a plain cookie, given the data, is 0.6, which makes it the posterior probability for that event. Okay, so this I think is really super important. And if anyone has a question, please raise it right now.
Chaitanya,
Yeah.
For example, if here you see that prior probability is 0.5 and posterior probability is 0.6. Now, if I take a bowl which contains, if bowl 2 and bowl 1 are same, like here, the only problem is bowl 1 is different from bowl 2 in terms of its composition, because it has 10 chocolate and 30 plain. For example, we take it hypothetically that it also, bowl 1 also has 10 chocolate and 10 plain, 20 chocolate or whatever it is. I mean, they are same, like 10 chocolate and 10 plain cookies. Then the posterior probability will again be 0.5, right?
Okay. So here is my response to that. Why don't you do this as an assignment?
Yeah.
Just apply what you said, right? Let's assume bowl 1 has 10 chocolate and 10 plain, okay? So just apply the same mathematics to your question and tell me what the posterior probability of that is. You don't have to do it right now, but just remember this and do it and let me know later what the posterior probability is.
Okay. Okay. But my gut feeling is 0.5. That's what. Anyway, I'll try it out.
I believe the posterior probability will change.
Okay, I'll try it out.
Because bowl 2 has more plain cookies. Right?
Okay. I got
anyway,
it.
You try it out, apply the formula, and see what the answer is.
Okay, right.
Yeah.
Chaitanya, can I just interrupt for a minute?
Sure.
Yeah. So I mean, I think the posterior probability will still be 0.5 because if you plug in the values into the formula, you'll realize that it can't be more than 0.5. But I just wanted to point out that if you're blindfolded and if you pick a cookie from one of those bowls, but you know that one of those bowls, which is bowl 1, has more plain cookies, and you have got a plain cookie, right? If you already have that information that bowl 1 has more plain cookies, then what you will, and if you are asked that which bowl you picked it from, your prior probability will be 0.5. You'll be like, oh, I don't know, it could be bowl 1 or bowl 2. But given that bowl 1 has more plain cookies, you will probably say that maybe it is bowl 1, because you are more likely to pick a plain cookie from bowl 1, right? So intuitively, what you have done in your mind is Bayesian inference.
Okay, right.
So you have your prior hypothesis, and but then when you look at the data, it's a plain cookie, and you also know that there are more plain cookies in bowl 1. Then you say I think it's 0.5, but I'm more inclined to say that I have probably picked it from bowl 1. I mean, your prior probability is that it's probably, I mean, it could be bowl 1 or bowl 2, but because there are more plain cookies in bowl 1, you are more inclined to say that I have probably picked it from bowl 1. So what you have intuitively done there is Bayesian inference.
Thank you.
Yeah, so basically what Praveen said in English, we did that mathematically here, right? So that's the whole idea of Bayesian inference. So Bayesian inference gives us the probabilities of different hypotheses in the light of the data, right? So regular probability does not have the light of the data in mind, right? It has no idea of the data, right? Cool. So let me move on to the next slide. So now here we are not really interested in cookies or bowls. Some of us are, but for us, what's important is trees and data as phylogeneticists, right? So what we do is we substitute hypothesis with tree and D with data. So the probability of getting a tree given the data is equal to the probability of the tree multiplied by the likelihood of the tree divided by the probability of the data. Okay, so this is how we kind of reduce the Bayes theorem for our use case, right? So let me explain this a little bit. So the probability of the data is nothing but the summation of the prior probability of the tree multiplied by the likelihood of the tree, right? For all given hypotheses. For example, I'm going back to the previous slide. You see the denominator over here, right? So if you have n, we have only two hypotheses. So the denominator has prior multiplied by likelihood for hypothesis 1 plus prior multiplied by likelihood for hypothesis 2. So if you have 10 hypotheses, we'll extend the denominator to up to 10, right? And summate all of them or add all of them, right? So that's exactly what we're doing here. So the probability of the data is basically a summation of the prior multiplied by the likelihood of every hypothesis possible, right? So in essence, can anyone tell me what the value of that would be, right? The prior of a hypothesis multiplied by the likelihood of a hypothesis for all possible hypotheses. So what do you think the denominator would be in the Bayesian algorithm or the Bayesian formula? So what is the sum of all probabilities for a particular event?
1.
Exactly. So each of these values, right? So prior multiplied by likelihood for each hypothesis, if you add all possible hypotheses, your denominator will tend towards 1. Okay, so that's one thing you need to remember with the Bayes formula, right? The denominator is not exactly 1, it probably tends to 1, right? It gets to maybe 0.98 or 0.99 or even more, right? Okay. So in essence, this is what our equation now looks like, right? Our Bayes equation. Now moving on. So, okay. So in effect, the posterior probability of a tree is equal to the prior probability of the tree multiplied by likelihood of the tree, right? Divided by the probability of the data. Now, what is the probability of the data? The data is something that we already have in hand. So the probability of the data is 1, okay? But when we summate all the hypotheses, we get somewhere close to 1, 0.99 or something, right? So this is actually the Bayes formula for tree building. So you don't have to memorize this. You can just go back and look at this presentation or just look at this video for the explanation. But in essence, this is what all programs that use Bayesian inference to get to a certain tree, this is the formula they all use, okay? So again, I need to mention here, like Praveen was saying, that the prior probability, like go back to the cookie example, prior probability is basically a state of knowledge or ignorance, right? So when you say, oh, what is the probability of picking a cookie from bowl 1? We immediately say 0.5 because we don't know the contents of the cookie. Contents of the bowls. right? And that is why it's called prior probability, because it's a state of knowledge or ignorance, right? However, posterior probability is a much more educated probability, because we now know the contents of bowl 1 and bowl 2, and we include what is called the likelihood of each hypothesis to deduct a more educated probability for a certain hypothesis, right? And that is what all Bayesian methods do. So this could be MrBayes, it could be Beast, it could be, you know, Bayesian phylogeography and phylogenetics, a whole bunch of methods that use the Bayesian approach, right? Okay, if no one has questions, I'm going to move on.
Hi, Chaitanya.
Yeah.
Yeah. So basically, it's talking about the posterior, the difference between the posterior and prior probability. Basically, is the clear-cut new information adding up. That's what he says. That's a more educated probability.
Yeah. So if you go back to the cookie example, right? If we just assume that there were just these two bowls and you could pick a cookie.
Hello, I just lost your voice, Chaitanya.
Chaitanya, even I can hear you.
Something like an approximation of calculating a posterior probability, right?
Sorry, Chaitanya, I didn't hear you properly before that.
Okay, was everyone else able to hear me, or?
No, there was
even I also missed a little bit.
Okay.
And others are also saying.
Okay.
So if you can just answer Shuvendu's question again.
Okay. So I was saying, I hope you all can hear me. So if I break, just flag me off, okay, please. So I was just saying that just like how Praveen explained it to us, if we are aware that there are two bowls and there are cookies in both bowls, right? And we are given we pick a plain cookie, okay? Now we intuitively say the probability that the cookie came from either bowl is 0.5, right? Because that's all we know, and that's very simple prior probability. However, in the light of the data in those bowls, right? Now, when the light of the data basically says that bowl 1 has 30 plain cookies, whereas bowl 2 has 20 plain cookies, right? Now, when someone asks you, which bowl do you think you picked it from? You will intuitively start thinking, okay, the probability now should be definitely greater than 0.5 for bowl 1, because there are more cookies there, more plain cookies there, right? So intuitively, you're trying to actually calculate prior probability, posterior probability in your head, right? So instead of doing it intuitively, we're just doing it mathematically here. Does that answer you, Shuvendu?
Yeah.
Okay. Let's move on.
Hello, Chaitanya. This is Shubham here.
Yeah, sure.
Yeah, I don't still realize why is the probability of the data just tending towards 1 and not 1.
Oh, it's because it will get caught in a little bit of decimals over there, you know. That's the only reason.
Okay.
Because you're summating the prior multiplied by likelihood for every possible hypothesis, right?
Okay.
And the sum of all those hypotheses has to be 1, because one of those hypotheses explains the data for sure, right?
Okay. And because it is just an estimation and we are assuming some variables here and there, and that is why we are not getting perfect one.
Yeah. Because some of that information gets lost in the calculation, right? In your decimals.
Yeah.
Right?
Yeah. Okay.
That's the only point. That's the only thing.
Okay, got it.
Yeah. Okay, moving on. Now, this is a slide that all of you are familiar with already. Roy spoke about this. So, so this slide basically takes you to the reason why we use heuristic methods and we don't use an exhaustive search, right? So if you look on the left, the number of taxa, right? For 2 taxa, there is only one possible rooted tree and one possible unrooted tree. And for 3 taxa, there are 3 rooted trees and one possible unrooted tree. But as you keep going, you see that the number of rooted trees and unrooted trees increase exponentially, right? So if you're dealing with a data set with 5 taxa, right, the number of possible trees is 3 into 10 power 74, and that's a ridiculously large number, right? Now, if you have to evaluate all these 3 into 10 power 74 trees, you will probably have to run the program, and you will eventually die, and maybe your grandson or granddaughter will get the results, right? Or what's even worse, by the time the program finishes running, these animals might have evolved into newer beings, right? So this is not an ideal situation to be able to exhaustively enumerate every tree. Okay, so so the people who implemented Bayesian inference, they came up with a heuristic method called Markov Chain Monte Carlo method. Okay, I'm just going to quickly like gloss over this thing because it's just a good to know for you guys. So here is how a conventional or an exhaustive search of tree space will happen. So let's assume that in this picture, these are all the possible trees for your data. Okay, we're just assuming, and this in its entirety is your tree space. Okay, and this beautiful tree here is the actual tree that you need, right? Or the tree with the highest posterior probability, or the tree that best explains your data, right? Now, an exhaustive search would start at tree number 1, right? And exhaustively look at all the trees in the vicinity till it gets to right tree. Now, if you're dealing with 3 into 10 power 74 trees, this method is going to like take a bloody long time, like we spoke about. So what did people do? They implemented the Markov Chain Monte Carlo approximation. So here is how the Markov Chain Monte Carlo approximation works. So let's assume we use 2 random chains. Okay, the 2 dots you see, the yellow dot and the red dot, represent the 2 Markov chains that we're going to start, and these chains start at random trees in your tree space. Okay, so one chain starts here and the other one starts somewhere else. Okay, now, and both chains, remember, are independent of each other and they will be running independent of each other. All right, so let's take this chain, the yellow chain, right? Now, once it's at a certain random tree, it is going to calculate the posterior probability of the tree it is at the moment. Okay, and let's say that posterior probability is about 0.8, for example. And then what it would do is it would make small changes to that tree, the present tree that it has. Basically change certain relationships maybe, right? And these changes are called perturbations. Okay, it will make small changes to the tree it is at presently and get to a new tree. Okay, and it will calculate the posterior probability of that tree, right? Now, if the posterior probability of the new changed tree is, let's say, 0.85, which is greater than 0.80, the chain will actually move to the new tree, right? So, and the same method is followed by the second chain in your analysis. So you're at a certain tree, you calculate the posterior probability of that tree, and then you make certain changes to the tree, perturbations as we call them, and you calculate the posterior probability of the changed tree. And if it is higher than your current tree, you jump there. Okay? And using this philosophy, we hope that the chains will keep going or jumping to trees that have higher and higher posterior probability, right? And the great big hope is that these 2 chains will converge onto the one tree that we need, which is the tree that, basically the tree with the highest posterior probability in your tree space, right? Does anyone have a question here?
Hi, Chaitanya.
Yes.
So if you say that the tree will put a posterior probability and it will modify the tree and put again revise the posterior probability and move ahead, and probably it will have a higher posterior probability in the next tree. So
Correct.
and it will move on and move on and to it goes to the best tree. Now if at any point it gets a tree which has lower posterior probability than it actually had from the previous tree, what is there any will it skip that tree?
It will not move to that tree.
Okay.
It will stay back at its present tree, okay, and it will make further perturbations or different perturbations to get to a different, slightly different topology, and then hope that that topology gives it a higher posterior probability.
Okay, great.
Right? Okay.
So what if the two trees have the equal posterior probability, if in a hypothetical manner, how that will work?
Okay, good question. I don't know how these algorithms resolve that. I probably have to look it up. But yeah, frankly, I don't know how it will resolve a case where.
Chaitanya, can I interrupt there? So you can have two equally parsimonious trees. In case of likelihood, you will, in case of methods that use the likelihood function, both maximum likelihood and Bayesian inference, you will never get exactly same values. You know, if there's a minor difference in tree topology, you will get different likelihood scores, and you will get different posterior probabilities. But parsimony, you can minor differences between trees, you can get the same tree length. So it's not a problem here.
Okay, so there's a question in the chat box. So Ashna says, how many such MCMC will be running? Will it be in such a way that it will analyze all the trees?
Okay, how many MCMCs will run? We will get to that, right? We'll look at it in the practical session. And sorry, what's the second part of the question?
Will it be in such a way that it will analyze all the trees? Basically, like complete tree space.
No, no. So that's one of the drawbacks of using a heuristic search algorithm, right? And actually one of the advantages too. So we don't have to enumerate all the trees. Because if you start enumerating all the trees, then it's going to be it's going to take a very, very long time. So we're talking about 3 into 10 power 74 trees for a 50 taxa data set, right? And that's like ridiculously large number of trees to enumerate.
Okay, there's one more question. Okay, Praveen's already answered.
All right. Cool. Moving on. So this chart again, it shows the Bayesian formula for n taxa. I'm sorry, for n hypothesis actually, right? So you have in the denominator, you see that it's h1 to hn. Like we mentioned earlier, the denominator always tends towards 1, right? So the Markov chain Monte Carlo approximation of posterior probability of trees, right? So the posterior probability of phylogenies can be approximated by sampling trees from the posterior probability distribution, right? We will see what that actually means in some of the forthcoming charts. And Markov chain Monte Carlo can be used to sample phylogenies according to their posterior probability. I think, yeah, it's basically the same thing. So basically, this Monte Carlo Markov chain, especially the Monte Carlo algorithm, came with all the was first invented for casinos in Las Vegas, I'm told, and from there on, it's been incorporated into software and for software to do all sorts of other things like calculate the right tree and so on, right? And Markov chain is basically a chain that moves from one state to the other, and we'll see what Markov chains are in the next slide. Yeah. Okay. So Markov chain is basically a process that consists of a finite number of states and some known probabilities. Okay. Let's say Pij, where Pij is the probability of moving from state I to state J. Okay. Now, don't worry too much about what that means. Just take an example again, right? If you see the flowchart on your right, or it's more like a state transition diagram, I would say. Let's say there are two milk manufacturing companies, Nandini and Amul, right? And we're saying that at present, on present day, Nandini has 0.6 of the market share, as in 60% of the customers are with Nandini and 40% of the customers are with Amul, right? So the way you interpret the state transition diagram is that given time, right, or given the next unit of time, the next unit could be, let's say, a week or a month or even a year, 0.9 or 90% of Nandini's customers stay back with Nandini because they like that milk so much. And only 20% of Amul customers stay back with Amul, right? Which means that 10% of Nandini customers, or 0.1 probability, they are moving to Amul. And probability of 0.8 that customers from Amul would move to Nandini. So this is a state transition diagram given all this data, right? And we today know that Nandini has 60% market share and Amul has 40%. So here we are basically trying to explain what a Markov chain is. So yeah. So you see the matrix on your left, right? So basically we have listed down the numbers over here, the numbers of the people staying with a certain brand and people moving. So the number of people who will stay back with Nandini is 0.9. The number of people, or the probability of people moving to Amul from Nandini is 0.1. And similarly for Amul, right? Now, for time t, which is today, we know that the market share is 0.6 and 0.4, right? But for time t plus 1, let us calculate at time t plus 1, let's say 1 week from now, how many customers or what market share will Nandini have and versus the market share that Amul will have, right? So how do we calculate this? We know that Nandini has 0.6. So 0.6 multiplied by 0.9, which is the probability of the number of people staying back with Nandini, right? So that is 0.54 plus the number of people moving from Amul to Nandini, right? Which is 0.4 multiplied by 0.8, which is 0.32, right? So 0.54 plus 0.32 is 0.86, right? Similarly for Amul, so it's got a 0.4 market share. So 0.4 multiplied by 0.2, which is the probability of the number of people staying back. So 0.4 multiplied by 0.2 is 0.08 plus the number of people who will move from Nandini back to Amul. So that's 0.6 multiplied by 0.1, which is 0.06. So 0.06 plus 0.08 is 0.14, right? So similarly, you can calculate the market share at t plus 2, t plus 3, and for n generations. So this is how a Markov chain can typically be used, right? So did everyone understand this, or do you have any doubts? Okay, crystal clear, I guess. So let's move on.
Chaitanya,
Yeah.
I just wanted to add, so what is going to happen if you run this chain for millions of generations? Can anyone answer that question? Will the share of Nandini go up to 1, or what's going to happen?
Nandini's share will go up to 1 and A's share will tend to 0.
But will it reach 1? Are you sure it will reach 1?
I'm not sure if it reaches 1, but it will definitely try to reach 1. It will tend towards that number.
Yeah, it will basically saturate at some point in time.
Yeah.
It will saturate at some point in time, right? So that is the point we want to get to when we run the Markov chain for tree building. I just wanted to add that. Yeah, Chaitanya, carry on.
No, that's a very important point, because we need that kind of saturation for our analysis to end and so on, because you can't keep infinitely running these chains. And because in the end, like if you take this example, I think that was Shubham who was speaking. Like Shubham said, Nandini will start tending towards 1 after millions of generations, and Amul will start tending towards 0, right? But Nandini will never become perfectly 1, and Amul will never become perfectly 0. Okay. But however, after a certain point, you realize that the numbers are not varying that much, right? So that is when we say that we have reached what is called stationary distribution. Okay. Now we'll see what all this is in the forthcoming charts, and we'll move on for now. Okay. So this again is the Bayesian equation, right? And here we'll introduce a new term called acceptance ratio, though we have already spoken about what acceptance ratio is, right? So acceptance ratio basically is like when you remember I was telling you that the chain starts at one tree, calculates the posterior probability for that tree. Let's say that tree is TC, okay? Tree current, okay? And then it makes some perturbations to the current tree and calculates gets a new tree, let's say T1, with a slightly different topology from your current tree. So basically what the program would do is it would calculate the posterior probability of that tree and see if that tree has a higher posterior probability than the current tree, right? So acceptance ratio is basically posterior probability of the new tree divided by posterior probability of your current tree, right? So this whole equation basically talks about that, but it's as simple as what I just explained: posterior probability of the new tree divided by that of the current tree. Now, if the ratio is greater than 1, then the program will move to the new tree, right? If the ratio is less than 1, the program will stay put, okay, and try and do a different set of perturbations to get a different tree. Okay, I hope this is clear. So similarly, we keep making these perturbations and we keep moving towards, the higher posterior values of posterior probability, and we run this chain for millions of generations, and eventually we hope that we will reach that stationary distribution that we were talking about, and we will get the right bunch of trees that all have the highest posterior probabilities. Okay, moving on. So this chart again basically explains the same thing. If the ratio is greater than 1, we make the jump from the current tree to the next tree. If it's less than 1, we don't make the jump. We basically stay put at the same tree. You notice this basically represents the same tree here, right? So that's what this means. I'm not going to spend too much time on this chart. Right, now let's talk about an ideal world. Okay, let's say you're from utopia. So in utopia, all your probability distribution will look like this, right? It will be a proper bell curve. Okay, so traversing a probability distribution like this. So here what we've essentially done is we are representing tree space in terms of their posterior probabilities, right? I hope you understood that. And here we have to basically traverse posterior probabilities, okay? And in an ideal world, you'll get this perfect shape. So let's say our starting tree is somewhere here, and this is the posterior probability of your starting tree, right? The little blue dot. And then you make some perturbations and move to the next tree, which has a slightly higher posterior probability, right? So you're slowly climbing up this little hill. And then your third tree is somewhere there, and your fourth tree is there, and so on and so forth, till you get to a bunch of trees that are right at the peak. Okay, so basically your Markov chain is climbing this little hill till it reaches this peak. Okay, And then it's going to sample the trees in this peak, assuming that all these trees have this very similar posterior probability. It's going to sample the tree space at this peak, right? And from this peak, do you think the chain can go anywhere else? So once this peak is reached,
I don't think it would. It will tend to go anywhere else because the ratio will not go beyond 1.
correct. So anywhere from the peak, right? Any direction you move in, your posterior probabilities are going to be lower, right? So you won't make that move, and you will stay right on top here, correct? So this is like the ideal situation of traversing probability space, where you reach the peak and you found your best trees, and you do a consensus of your best trees, and you get the tree that you want, right? Everyone with me so far? So it's like that English proverb, right? When you're at your highest, the only direction you can go from there is downwards, right? So you really can't go any higher than this. So, however, we don't live in a utopian world. We live in a world where probabilities are as messed up as our politics, right? So typically probability spaces would look something like this, right? You don't get that perfect bell curve. You look at this probability space, this is actually a closer representation of what programs have to deal with when they're dealing with posterior probabilities of a given set of trees, right? So you see that there are multiple little peaks here. So there is a peak called E, there is C, A, D, F, and so on, right? Now, here's a scenario where, let's say, your Markov chain starts here. See where my mouse is pointing at that little circle. Your Markov chain starts here, and it does some perturbations, and it starts climbing this little hill here, right? And then it keeps climbing and gets to the top of this hill, okay? But here, from here on, the Markov chain can't go anywhere, right? Because every other point from this hill is lower, right? So at this point, this Markov chain is basically stuck. It is stuck at this peak. But is this the highest peak in your probability space? No, right? The highest peak in your probability space is here, right? A is your highest peak. So your Markov chain should have ideally gotten here, but unfortunately, because it started on the wrong hill, it got stuck in B. Okay? So how do we solve this problem? So I'm just basically going to try and explain a little about how programs like MrBayes and all fix this problem. So this is a problem called the local optima. So where your Markov chain reaches a local optima, and from there is no way down, but it's not really found the bunch of trees with the right posterior probabilities or the highest posterior probabilities in your tree space. Okay, so we'll just quickly see how a program like MrBayes would fix this problem. Yeah. Any questions on this?
This is Shubham here.
Yeah.
So is it possible that we have multiple global optima?
No. There can be only one global optima.
Okay.
There could be multiple local optimas, of course. Okay, now let's see how some of the programs fix this problem, right? Okay, now let's say this robot here represents your Markov chain, right? Now, so what will the robot or the Markov chain do for the proposed uphill step? Okay, if the proposed step is of higher elevation, it will accept the move automatically, which means if the proposed step is to a tree with higher posterior probability than the current tree, it's a no-brainer, right? I will just move. However, what happens when the proposed step is a downhill step? Okay. Now, what the program will do is it will calculate the acceptance ratio. of even the downhill step. Let's say my current tree, the posterior probability is 0.9. I'm sorry, let's say 0.9. Okay, and the next step I have to go to is for a tree that has a posterior probability of 0.7. Right now, 0.7 is less than 0.9. So should I move or not? Right. So it uses a very simple method to decide whether it should move downhill or it should not. Right. So what it does is it calculates 0.7 divided by 0.9. Right. And then I think that value is about 0.85. Let's say it's 0.85. Okay. Now it also generates a uniform random number between 0 and 1. Any random number, right? So now if I have to pick a random number, I'd say, okay, 0.65, for example, right? That's between 0 and 1. Now, if 0.85, which is my acceptance ratio, if that's greater than the random number that's being picked, then I will make the move, even if the move is downhill. Okay. However, let's say I pick 0.95 as the random number. Now my acceptance ratio is less than 0.95. So I will not make the move. Okay. So now the idea behind this is, if the downhill step that I'm making is small, I'm just taking a very small step downhill, the algorithm will allow you to make it. However, if the downhill step is huge, let's say it's like falling off a cliff almost. If it's a large downhill step, then the algorithm is going to reject that move and try and perturb the current tree a little more and get to the and find the next possible tree. Right? Is this clear? No questions? Great.
Excuse me. But in the previous picture, the local optima was the global optima was very much far from the local optima. So how come it will reach the global optima?
It will reach slowly. There's no hurry, right? Because we're going to run these chains for hundreds of millions of generations, right? So eventually it will reach there. Okay, so that is the hope, at least. And there are ways of reaching there quickly also. We'll see in the next few slides. I hope this part is clear about how a small downhill step is made, whereas a large downhill step is rejected, right?
Chaitanya, could you also elaborate on why these small downhill steps are needed? You know, why not just use the acceptance ratio and keep going up?
Yeah, in the upcoming slide.
Okay.
Right. So in the upcoming slide, it'll all become very clear about why we need small downhill steps. Okay. Cool. Now look at this slide. Here, you remember when we did that Markov chain simulation in one of the previous slides, we ran 2 chains, right? Here, assume there are 3 chains that are traversing your tree space simultaneously. Okay. The first chain is called A, represented by this robot here. The second one is called B, represented by this robot, and C. Okay. Now, why do we need 3 different chains, and what is the actual funda and what's going on, right? So there's this convoluted formula over here. Don't worry about that too much. I'll just explain that in English to you. For each chain A, B, and C, we apply what is called a temperature. Okay, and this temperature is applied on the entire probability space. Okay, and the temperature is basically represented by this parameter beta. Okay, so basically you take your entire probability space and put it to the power of beta. Okay, the value of beta will change for every chain. For A, it will be a different value. For B, it will be different, and C, it will be different, right? For A, which is chain number 0, beta will be 1. Okay, and anything x raised to the power of 1 is x, right? So chain A will visualize the probability space as it already is. So chain A basically does nothing. It doesn't make any changes to the probability space because its beta value is 1. But chain B, the beta value is actually a fraction, which is less than 1. Okay, and so for chain B, what happens is the way chain B perceives the probability space, it looks as though the probability space has melted. You see these tall peaks here, over here, but for chain B, the peaks are smaller, right? Similarly, for chain C, it's further melted down. It almost looks like plain land for chain C because the beta value is a higher fraction and the probability space is like almost plain land, right? Now, these chains, if you look at what I just explained in context of the previous slide, all these chains can make small downhill steps, right? All these chains can make small downhill steps to traverse probability space, right? But for which chain would it be the most easy to traverse probability space? Can someone unmute and answer? So amongst chain A, B, and C, for which chain would it be the most easiest, given the context of the previous slide?
C.
Can you explain why?
C.
Because it is more like a plain land. No uphill and downhill. Dilute.
I can't hear you clearly.
It is more like a plain land because no uphills and downhills are there because of the melting.
C is correct, but C is more likely to traverse the probability space better because it can take small downhill steps here because there are no large uphill steps, right? As opposed to A, which might have to take large uphill steps, right? And that is why the algorithm differentiates between a small downhill step versus a large downhill step, right? So for C, it's easiest to traverse probability space, followed by B, and it is actually hardest for chain A to traverse probability space because there are some huge downhill steps in this, in this contour, right? I hope everybody understood this. So a program like MrBayes would have 4 Markov chains running independently, okay? And each chain would have its own temperature, which means for each chain, the probability space has been melted down a little bit, except for the first chain, right? Whose probability space is basically the same as the real probability space. I hope that is clear and I didn't confuse you guys. Okay. Now,
Chaitanya, if I can add, and the reason we do this melting business is to make sure that the Markov chain samples larger tree space, larger probability space, and does not get stuck in one of these peaks.
yes. So obviously, like Praveen said, chain C has a much better chance of traversing more trees, right? Or more of the probability space than chain A, which might actually get stuck in local optima. So I'd like to introduce 2 new terms here, very simple terms. So typically chain A is what we would call a cold chain, okay? And chains B and C, because basically it's called a cold chain because it does not carry a temperature, because the beta here is 1 and the probability space remains as it is. But chains B and C are called hot chains or warm chains because they carry a certain temperature value that melts the probability space down, right? Now, what is the actual use of hot and cold chains? We'll just see in the next chart, right? Now, assume that your cold chain or chain A from the previous chart has reached this local optimum, right? It looks a little confused right there on the peak because there is nowhere else to go and it's kind of stuck there. But one of your hot chains, let's say chain C from the previous chart, has actually reached a peak which is higher than your cold chain, right? So your hot chain C has reached here, which might be the global optimum. I'm just saying might because it might not also, right? At this stage, what happens is these 2 chains, the cold and hot chain, will communicate with each other, right? And once the program realizes that the hot chain is at a higher posterior probability than the cold chain, the program will basically swap chains. In the sense, this robot here will become the hot chain, and this will become the cold chain, and it will remain there. And the hot chain will start traversing probability space again. Because for the hot chain, this peak is not really this high, right? And the cold chain will basically have gotten to a position of higher posterior probability than it previously was. Simple enough. So this is how the swaps between hot and cold chains happen, and this is why they happen. And if we run enough number of chains, let's say 4 or 8 chains, we hope that some of the heated chains will get to, you know, the global optima and swap with the cold chain, and we will get our trees with the most, with the highest posterior probabilities over there. Is this clear? Any questions? I guess not. Okay, I'll move on.
There are no questions on the chat box.
Okay, I'll move on. Cool.
Okay, so Shruti says, how is the temperature determined?
Determined. Okay. So, well, I was hoping nobody will ask this question, but now that you've asked it, now, so this is how the beta parameter is calculated using this formula. When we run MrBayes, you'll also see that it shows you this formula, right? So here you see a value I, okay? So I is nothing but the number of the chain. So for chain A, the value of I is 0, right? So you substitute 0 at I instead of I. So what you get is T multiplied, and T here is approximately 0.2, right? Oh, I'm sorry, I made a mistake in this chart. A is actually 1, okay? It's not 0, it's 1. So if you substitute I with 1, you'll see that this whole value becomes 1, right? So beta becomes 1, and you basically take your prior posterior probability and raise it to the power of beta, which for the cold chain is 1. So your posterior probability does not change. However, if you look at chain 2 and substitute I with 2, you get a fraction here, right? So 2 minus 1 is 1, and T is 0.2. So this is 0.4. 1 plus 0.4 is 1.4. So this is 1 divided by 1.4, which is a value less than 1. So you raise your posterior probability to a fraction less than 1, you will get a reduced posterior probability, right? So it will basically look like the posterior probability has melted. Similarly, the higher number of your chain, so chain 3 and 4 will have a higher temperature, therefore will melt the probability space a little more, right? Is that clear, Shruti? Guys, am I on? Am I audible?
You're on. I'm just asking
you
people to unmute and ask.
Okay. So, but I just hope this is clear.
Okay. So Shubhendu Das has a question.
So hi Chaitanya.
Hi.
Yeah. So basically, moving cold chain to hot chain shifting is like shifting towards the prior to the posterior probability, right?
No. So
Okay.
the cold chain has sampled a tree or a group of trees with certain posterior probability. Okay, and the hot chain has also sampled a bunch of trees with posterior probability, or maybe one tree with posterior probability. However, in this scenario, we realize that the hot chain is at a tree with higher posterior probability than the cold chain, right? And then there is a communication that happens between these two chains, and then there is a swap. The current cold chain becomes the hot chain, and the current hot chain becomes the cold chain, right? Is that clear?
Okay.
So we are only dealing with posterior probability, dealing with prior probabilities here.
Okay.
Because for every tree that we sample, we are going to be calculating posterior probability using the prior probability, yes, but the optimality criteria, as we spoke about, is really the posterior probability for Bayesian inference, right? So that's the value we are trying to, better and better and better with each generation of the run. Yeah.
Okay.
Another way of looking at it is, if you're running just two chains, and but then ultimately you want one tree, so you can't be sampling from both the chains, right? So basically you pick the best tree in each of those chains, and so you're sampling only from the cold chain. So every time the hot chain gets a better tree, you start sampling from that hot chain, and your cold chain now becomes a hot chain, and and the process continues. I don't know if that makes sense, but when we run MrBayes, hopefully this will become clear.
Yeah, so I'll just add to what Praveen said. I'm just going back a few slides, and sorry about that. So if you look at this slide at the bottom, it says we run the Markov chain for millions of generations, and every 100th generation is saved or sampled. Okay, so we keep running the Markov chain, and every 100th generation that we encounter, the parameters are saved. Basically, the tree, the posterior probability, and the other parameters are saved. Right now, this sampling every 100th generation happens only for the cold chain. Right? We don't sample from the hot chain. So all the tree samples that we get in the end are sampled by the cold chain. The hot chain is only to basically traverse your tree space and keep informing the cold chain of higher peaks. That's all the function of the hot chain is. Whereas it's the job of the cold chain to sample every 100 generations and report back the samples to us, right? Okay, let me move on.
Okay, Chaitanya.
Yeah.
So in this hot chain, it will traverse the whole length, and wherever it will find peak, it will just tell the cold chain, okay, there is some, I see some peaks here, you have to sample here.
No.
Does it like that?
No, it will reach the peak first.
Okay, it will reach the peak, and then it will tell the cold chain.
It will evaluate the posterior probability, right? And then it will communicate to the cold chain saying that, hey, look, I am at posterior probability 0.95, right? And the cold chain will say, oh, I am at posterior probability 0.75. So let's exchange places, right?
Okay. Okay, got it.
Okay. Okay. Moving on. So basically, to avoid getting stuck in local optima, we already saw that, run several chains, all heated chains that have the ability to melt the probability space, except one cold chain, right? The cold chain is used for sampling posterior distribution of interest, and only the cold chain is used for that. Heated chains provide the cold chain with intelligent proposals of new states, and that is all that the heated chains do, apart from traversing the probability space more efficiently, right? Okay. So I guess that is the end. Oh no, it is not the end of the presentation. Okay. So once your runs are done, right, and your cold chain has sampled every 100th generation, and it's given you a bunch of samples, right? So like Praveen was talking about in the Nandini and Amul example, right? Same thing will happen with sampling posterior probabilities of trees. So initially you will see that your graph kind of is growing like this, right? It's not stationary or stable. The likelihood score is constantly increasing as your number of generations go up, right? And at a certain place, the graph flattens, right? So here, once you've reached the stationary distribution stage, even if you run another 100 million generations, this is not going to improve, right? Your likelihood is going to remain here or in the vicinity over here, right? So this is what is called stationary distribution of parameters that you're interested in. And ideally, when you sample when you're trying to enumerate your final tree or your consensus tree, you should be using only samples from the stationary distribution, right? And MrBayes gives you a very easy way of discarding all these unnecessary samples and getting straight here to the stationary distribution, and we'll see how to do that. Okay. Now there's a program called Tracer, which I missed sharing with you guys. Maybe after this session I'll share it with you. So you can actually look at log files and things like that, and any file that has a uses a Markov chain to sample. It will show you a graph like this, and based on that graph, you can choose where to draw your burn-in cutoff. Right? You can say, okay, I want to discard the first 20% of my trees because they were all noise and it was not in stationary distribution. And I'll only take the last 80%, or I'll only take the last 75% of the sampling and build a consensus tree out of that. Right? So this is what this chart is trying to show. I'll move on. So we'll just quickly look at maximum likelihood versus Bayesian inference. Like we spoke time and again, likelihood is probability of the data given the tree, where posterior probability is the probability of the hypothesis given the data. Right? Similarly, maximum likelihood method tries to maximize the probability of observing the data given in the tree, and it searches for the best tree. Right? And the Bayesian, we try to maximize posterior probability. So the optimality criteria is slightly different. Some comparisons again. So I think you can kind of, it's all self-explanatory. We've already spoken about a lot of these. One good thing about the Bayesian approach is it can use a complex, it can use a whole gamut of models of sequence evolution, right? But a program like RAXML can use only GTR and some of its variants. Though I'm told that RAXML these days can accommodate other models too. And so yeah, so that's one of the drawbacks of RAXML version 1.3 at least. Right?
And Chaitanya, there's another advantage of using Bayesian inference, at least in the way it's run in MrBayes, and that is you get posterior probability for nodes also. Whereas in case of maximum likelihood, you'll have to run bootstrap replicates.
Yes.
Yeah, and also in likelihood, the way likelihood works, it uses whatever heuristic function, and it gives you one tree which is completely resolved. That may or may not be the tree with the highest likelihood. It just depends on whatever heuristic function that you're using. But Bayesian is much more robust because it actually looks at multiple sets of trees. And what you can be sure of is almost all of these trees are going to be around the same peak that Chaitanya was talking about. So that way it becomes much better.
And all these trees will pretty much be topologically similar, right? There will be very, very, very minor changes, that too not in the topology, not in the overall topology, when you're dealing with a bunch of trees with high posterior probability.
Yeah, and also the changes in tree are not necessarily just topology. There are changes in branch lengths also with the same topology.
Yeah, and MrBayes also calculates posterior probability for branch lengths. So yeah. Cool. So I guess that is the end of the theory session for today. Does anyone have any questions?
I have sent Tracer to everyone in the WhatsApp.
Okay, great. Cool. So we'll just take any questions if anyone has on whatever was covered so far before we move to the practicals.
I have one question. So in short, maximum likelihood as well as Bayesian analysis, Bayesian inference gives a tree which has maximum likelihood and Bayesian ratio means at every node we will get one value. So will it give the most apted value for every node? Did you understand my question?
No, I did not actually.
For every node, for every branch length, I mean, for every node, we get one value, likelihood value as well as Bayesian inference. So these two programs, two programs give the trees with the most apted value for every node.
For every branch, yes. So that is only when the tree topologies for maximum likelihood and Bayesian are the same, which in all likelihood they will be. I think very, very few cases where the topologies might differ between, let's say, Raxamel and MrBayes. And then you have a consensus topology built on two different approaches, and then you can enumerate every branch with bootstrap and posterior probability.
Okay.
Is that what you were asking?
Okay.
However, if the three topologies are different from two approaches, you will have to present both topologies.
Sorry, I didn't get you. Sorry.
Your voice is breaking.
Sorry, I didn't get you. What you told just before, I didn't get you.
No, I was saying that if Raxamel and MrBayes gives you the same topology, tree topology, right? Then you can use that single topology because that's a consensus topology between these two completely different methods of tree building. You can use that topology to represent both, and you can quantify your branches using bootstrap and posterior probability.
Oh, okay.
So against every branch, you'd probably say 100/0.98, where 100 represents bootstrap value and 0.98 represents posterior probability.
Okay.
Right? Yeah.
Here, can we make a comparison between 100 bootstrap value and 0.98, where 0.98 is more accurate?
See, Roy explained how bootstrapping works, right? So you create bootstrap replicates. Let's say you create 100 bootstrap replicates, right? And for each replicate, you figure out if, let's say, the branch in question leads you to species A and B. Basically, species A and B are monophyletic, right? So for 100 replicates, how many times do you recover that branch B1, which leads to species A and B? You get my point? So out of 100 replicates, if that branch that leads to A and B is recovered 95 times, your bootstrap value is 95. Right?
Yeah.
So similarly, posterior probability, you have a bunch of trees with the highest posterior probability, right?
Okay.
And MrBayes builds a consensus tree, right? It builds a consensus tree out of all these trees with highest posterior probability. And then it checks how many times this consensus tree has been sampled during the running of the Markov chain, right? So if we have 100 samples, right, and this particular tree topology has been sampled 98 times, then the posterior probability of that tree is 0.98. Right?
I'm not sure I'm getting it totally, but I'm okay. Okay, I am partly getting it. I'll come to it again. I think I'll get it then.
Yeah, I think it will be clear when you run the program. Also, sorry?
You're breaking.
Okay. So I said, I think it will be clear when you run the program. Another thing is that if there are relationships that have less than 0.5 posterior probability, then those relationships are going to be unresolved. Chaitanya, you want to talk about unresolved?
Roy, you were in a relationship and then you broke up, man.
Thanks. I'll pass it on to Geeta.
Yeah, if I can just get here, the main difference between bootstrapping and posterior probability support for different branches is in case likelihood when we bootstrapping,
Sorry, Praveen, your voice is breaking.
those my voice is breaking. Okay, I don't know. Is it clear? The rest of you can hear me?
Now you're better. You can actually go on.
Yeah, okay. So in case of bootstrapping, what we are doing is we are creating 100 replicates of the data set, right? And then for each data, we build a tree and then figure out in how many trees that particular branch has been recovered. But in case of Bayesian approach, we are not coming up with 100 replicates. Instead, we are sampling from posterior probability distribution that has attained stationary phase, and that distribution has millions of trees, and those trees are summarized, and in those trees, get how often a particular branch has been recovered. And that gives us the posterior probability of that branch. So, you know, I hope it is clear from this.
Yeah,
Can
so
people hear me?
Yeah, I think it's
Yeah,
much
so
clearer.
it's basically, in Bootstrap, you're looking at, you're doing multiple pseudo replicates, whereas in posterior probability, you're looking at the frequency of that relationship occurring.
yeah.
So technically speaking,
So basically the
sorry, I'll just quickly finish this. Technically speaking, bootstrapping and posterior probability support for a particular branch, these are very different, you know.
Yeah. So see, the funda is the same, okay, but the methods used to arrive at support values between bootstrap and posterior probability is different. So that is the only thing you need to appreciate here, right?
Hey Chaitanya, so if you have some unresolved tree available on your computer, if you can just show it, then yeah, that'll be better. Because if it's less than 0.5,
What do you mean under
tree with polytomies.
A tree with polytomies. Oh, I really have to search, Roy. I don't know. Okay, if I find one, I'll share it with the group later on, right? Okay, I think we should move on to the practicals. So how do you want to do it? Does everyone want to do this with me, or you just want to watch my screen and you do it later?
Let's just do a demo. People can follow the video. I think that'll be better, given the bad internet connection. And
yeah. But everyone is able to hear my voice clearly, right?
I am. Yes. People say yes.
Okay. Shruti says yes. Anil
Yes.
Kulkarni says yes. So let's wait till we get to bootstrap greater than 90. Okay, cool. So let's start with the practicals, and so we're going to run a program called MrBayes, which basically uses Bayesian inference to figure out the tree with the highest posterior probability given the primate dataset, primate SITP dataset that we used for our previous exercises. Okay, so I'm just going to open the folder. Sorry. Okay, so you'll see this folder called MrBayes in your practicals folder, and you also will see an exercise sheet in that main folder. And basically, this exercise sheet lists all the commands that you need to be able to successfully execute MrBayes. All right. So you open the MrBayes folder again, and you will see a few executables. You watch where I'm pointing. There is underscore x64 underscore x86 underscore x86 underscore winxp. Now all these are MrBayes programs, but one is for 32-bit Windows, one is 4-bit, and the other is specifically for winxp. I don't know why. So whichever executable out of these three works for you, just run that, right? And all are basically the same program, just that they've been compiled for different processors. Okay, so let me run x64, which I think is a 64-bit one. So it opens up a screen like this, and it gives you a MrBayes prompt. All right. Now, unlike RAXML, MrBayes takes in what's called a nexus format. You see this? There's a file here which is called primates, and it's got file type nexus, right? So we'll be using the nexus format, and there are a lot of software that can help you convert from filelib to nexus, FASTA to nexus, and nexus back to filelib, and so on and so forth. So Genius does that. There are so many other softwares that do that. So you need a nexus file to be able to run MrBayes. That's the bottom line, right? Now, so the first step is I will run a command called execute. I'll say execute primates.nex. Okay, so this is the equivalent of doing load alignment in RAXML. All of you guys did that, right? Load alignment or import alignment, and then the alignment gets loaded. So this is the equivalent of that. So when I say execute primates. Importantly, the primates.nex file should be in the same folder as your MrBayes executable. Okay, so if you have primates.nex in some other folder and MrBayes in some other folder, it's not going to run. Or you have to give a proper path name here. I don't think it even takes path names and so on. So it's better if your nexus file is in the same folder as MrBayes. Okay. Now I say execute primates.nex and press enter. Let's see what happens. So a bunch of things have happened here. Okay. So it says executing the file primates.nex. Longest line length is 1165. Okay, and it shows you a few of the variables that are already set in MrBayes, and it says defining new matrix with 11 taxa and 1140 characters. So basically, this should match your data set, right? If it does not match your data set, there is some problem with your nexus file, and you probably have to recreate your nexus file. So here, MrBayes has basically read my nexus file and said there are 11 taxa, and the number of characters in each sequence is 1140. So this should be accurate. You need to be, you need to be awake when all this is happening. And here, it also gives you some seed value and so on and so forth, basically to be able to start your Markov chains and things like that. Now, I'm going to revert to the exercise sheet that's been shared because, frankly, I don't remember these commands by heart, and you also don't have to remember them by heart. The exercise sheet will tell you the syntax. So I'm going to revert to that. Okay. So we have done execute filename.nex, right? And the next step is to define partitions. Okay. So just like we did for RAXML, we can divide our data into partitions and assign separate models for each partition. It's the same funda as RAXML, but character-based interface as opposed to RAXML, which is a GUI, right? So I'm just selecting the first command and copying it. Okay, and I go and paste that command. So when you have to paste command prompt, for people not very used to working on the command prompt, you go to the top of the window where you see this bar, right? And you press right click. And then you'll get this option called edit, which will lead to the paste option. Okay, that is the only way to paste using any command prompt, even if it is a DOS command prompt. Okay, so I click on paste, I get that same command over here. So essentially what we're doing here is we are defining a partition called P1, which ranges from 1 to 600, maybe in the first gene, and which is a protein coding gene, and we are saying that codon position 1 belongs to partition 1. Similarly, codon position 1 of gene 2 or marker 2 is also part of partition 1. Okay. Now, where would we have got this information to be able to say that codon position 1 from both genes should be allocated to partition 1? Can anyone unmute and tell me?
Partition finder.
Exactly. So you get this information from partition finder. So that is why we are grouping codon position 1 from both genes into partition 1. And then I press enter, and it says something like defining char set called P1. Okay. Similarly, I try to define partition 2. So we are basically assigning codon position 2 from both genes to partition 2. And then we pick partition 3. Right? So now our 3 partitions have been defined. Now we try to define something called, we basically say our partitioning scheme is a scheme called gene for some reason. Right? I'll just put the command here and then explain it. So here basically we are saying we are using another command, MrBayes command called partition, saying that the partition scheme. One second, I just scroll down. So the partition scheme is called gene, and it's made of 3 partitions, and those 3 partitions are partition P1, P2, and P3. Right? Now MrBayes already knows what P1, P2, and P3 are because we have already defined them here in the earlier steps. Right? Now let's just enter and define the scheme called gene. Right? So now it says defining partition scheme called gene. Okay. Now we're done with all of that. Okay. Now if you look at the exercise sheet, which is in my screen, you see this rectangle here, which is basically all the commands we just executed. Okay. Now, in your Nexus file, there is an option of just specifying these commands right there. You don't have to execute these commands at the MrBayes prompt. You can just add these commands to your .next file at the end. Now, how will the program know these are MrBayes commands? Because you specify something like begin MrBayes semicolon. And then MrBayes knows that, okay, these are actually MrBayes commands. And then you define the char sets and the partitioning scheme, and you also do set partition gene, right? We haven't done set partition gene, so let's just do that. Okay, so once you do set partition gene, it tells you that setting gene is the partition, dividing characters into 3 parts, setting model defaults. So MrBayes assumes that you're not going to assign models for these partitions. So it's basically setting some default models. And the seed for generating default values is some random seed. Next, I go back to the exercise sheet. Okay, so the next command is to actually assign models to each partition. Okay, it is done using the lset command that I'm highlighting right now. Okay, so there are 3 options: nst is equal to 1, nst is equal to 2, nst is equal to 6. And lset, in case you want to do the GTR plus I, for example, you can say LST rates is equal to INV gamma. Now, how do we invoke this, right? This is how we do it. So lset apply to 1, 2, nst is equal to 2, rates is equal to gamma. Okay, I'm going to come back to this. Paste. So this is the command. So essentially what we're saying is we are, for partitions P1 and P2, we are applying nst equals 2 and rates is equal to gamma, right? Now, what does nst equal to 2 mean, right? So NST is equal to 2 means it's either the K80 model or the HKY85 model, right? So we are basically assigning K80 or HKY85 to partitions 1 and 2. So we do that. Now we are left with partition 3, right? So we copy the command for the lset command for partition 3. Paste. So here again, it's applying either K80 or HKY because NST is again 2. But let's, for fun, change this to NST equals 6. Okay. What does NST equals 6 mean? It corresponds to GTR substitution model. So just for fun, I'm using GTR for my third partition, and I press enter. Okay. Here's the question, right? Whoever answers this question correctly, you'll have to send me your postal ad, and I will ship a box of chocolates to you. And I'm not kidding. Okay. Can anyone tell me what does 1, 2, and 6 mean? Why is there no 3 or no 4 or no 5?
They are variables.
So we say NST.
The rate at which the nucleotide is evolving.
Parameter, number of parameters.
They are variables.
Okay, that's the wrong answer.
Variables.
Someone else. Jayalakshmi, you're breaking.
They are variables.
The number of substitutions.
Sorry? Okay, do one thing. Just type it on the chat and someone can read it out.
Okay, so so there are the answers are number of variables, number of parameters, and number of substitutions. Jayaditya says number of
variables. Okay.
Jayalakshmi says number of variables.
Roy, you're also breaking, man. Okay, wait. Let me just quickly look at the chat so that I understand what's going on. So Jayalakshmi says number of variables. Neha says number of substitutions. Dipandita says nucleotide substitutions. Jayaditya says number of parameters. Okay, so what variables are these? Okay. Okay. So I'm going to give it to Shubham because he says it's the substitution rate. So what substitution rate in nucleotides?
Meaning how three different positions are evolving. That is, the first one and second one may or may not evolve as fast as the third one.
Okay, you're wrong. That's the wrong answer. Okay, Ashna says substitution types of the model. So Ashna, can you unmute and explain your answer, please? I mean, this is not absolutely important. I'm just doing this for kicks, okay? I don't know if Ashna is typing or she's going to. She has an audio problem. So you can just type on the chat what you mean. Okay, well, let's just, okay. So it says, I thought 1 may be equal to probability of all bases in the respective model. That again is the wrong answer. No one has got this right. I think I have to ship a box of chocolates to myself. So basically what this means is, so why does NST equals 1 for F81 or JC or Jukes-Cantor? Because Jukes-Cantor and F81, Felsenstein 81 use only one substitution rate, right? There is only one parameter there. Whereas Kimura and HKY use 2 parameters, transitions versus transversions. GTR uses 6 parameters, right? Every possible pair has a different substitution rate, right? So A to T will have a substitution rate, A to C will have a different substitution rate, and so on. So GTR uses 6. So that's really what NST equals 6 means. All right. So let's just move on. Now that we have set the partitions, or we have set the models for each partition, we can figure out how to run MrBayes. So I'm going to type
Jayaditya feels cheated because apparently he told that.
Jayaditya said number of parameters. What parameters when nothing? That is not cheating, Jayaditya. You should have like explained it better.
Yeah, I should have.
Okay. Cool. So I'm just going to run this command called help NCMC. So NCMC stands for Markov Chain Monte Carlo, right? And so help NCMC will basically give you the exhaustive list of parameters that this command can take, and you don't have to remember all these parameters. Let's just do that. The important parameters, a lot of parameters went past. They scrolled past the screen. You can take a look at all of that later. The important ones are here, right? The parameter called nggen, which basically means how many generations you want to run the Markov chain for. That is the most important parameter. N runs is how many runs. Do I want to have 1 run or 2 runs? It does not mean the number of chains, right? N chains is the number of chains per run. Okay, so if I say n runs is equal to 2, right? So basically what I'm telling MrBayes is run 2 chain, what do I say? 2 versions of Monte Carlo Markov chains with 4 chains each, right? Each run will have 4 chains each. That's what this means. So for our case, let's run NCMC for a short duration so that we don't have to sit here all night. And so maybe what, Roy, do you think we should run for about 100,000 generations?
50,000 is fine. 50,000 will get done very soon.
Okay. No, anyway, even for 20,000, it kind of
it saturates very soon, so it should be fine.
Yeah, no, I just want to be able to talk through those, through that thing when the chains are running. So maybe I'll run it for about, yeah, 50,000 is fine, I guess. Let's run it for 50,000. So I'll type a command ncmc space nggen equals 50,000, right? So I'm telling MrBayes to run both runs, right? Do 2 runs, and both runs will run for 50,000. Both runs will initiate 4 Markov chains, and each of these 8 chains, 4 plus 4, will run for 50,000 generations. That's what it means, right? So now I'm pressing enter. It gives you a whole bunch of stuff, and it gives you initial log likelihoods, log priors, and all that. So you can take a look at all this from the log. And now it's asking me if I want to. Someone is unmuted, and there is an earthquake happening. Thanks. Okay, so do I want to override the results? Yes, let me just override. And now you see the chains will start, right? And it is by default sampling every 1,000 generations. And that also you can specify in your parameters when you're running NC. If I want to sample every 5,000 generations, I can do that, right? Now, here you see a star, right? So this star, this line of stars basically divides the first run from the second run, right? And if you see, each run has 4 log likelihood values that it's throwing out. And each of these represent the chains, the 4 chains. So there are 4 chains in run 1 and 4 chains in run 2. Also, interestingly, you'll notice that amongst the 4 chains, there are 3 chains with regular brackets and 1 chain with square brackets. Can anyone tell me what that means? Make a loud guess.
It's the highest value.
Not the highest value.
Cold chain and hot chains.
Exactly. So the square brackets, no chocolates though, okay? But yeah, so the square brackets represent the value in the square bracket represents what the cold chain has sampled. The log likelihood of the of what the cold chain has sampled. The regular brackets are the hot chains. Yeah, and you see that there are 3 hot chains and 1 cold chain for both runs. And all these are log likelihood values. And if you notice, the square brackets keep changing position, right? If you notice in this run, the square brackets are in the first chain, whereas here they are in the last chain. Can someone unmute and tell me what's happening?
Just like you had said, the hot chain and cold chain. At one point, if the cold chain is hot chain is at the highest point, it will swap places.
Correct. So that's exactly what's happening. So that's why you see the square brackets at different chain numbers. Basically, the hot and cold have swapped positions, right? Cool. So this has to run for another 16,000 generations, which I think it will complete fairly fast. And you also see this other interesting thing. It says average standard deviation of split frequencies is 0.003843, and then later on it becomes 0.004910. So what this basically means is the program is comparing the 2 runs, the sampling from the cold chain from run 1 with the sampling from the cold chain from run 2, and it is using some method to figure out if these 2 runs are converging around the same tree or around the same set of trees, right? Now, generally, what MrBayes recommends is if this value, this average standard deviation of split frequencies is 0.001 merged, and they've reached a consensus of the set of trees that you need with the highest posterior probability, right? Is that clear? But now we have already converged because we are at 0.004.
Your voice broke. Can you repeat the whole line again?
Yes. So you see this line called average standard deviation of split frequencies. Okay. So this basically is a comparison between chain 1 and chain 2. Sorry, run 1 and run 2 to see if the 2 runs are converging at the same set of trees, right? And if they are converged, MrBayes says that the average standard deviation of split frequencies, this value should be 0.01 or less, right? And here we see that it's already at 0.005, which means we have converged very easily. Is that clear?
Chaitanya, I also wanted to wait. Let's. Is that clear what Chaitanya just said?
Yes, yes.
I also wanted to add one other thing. Probably Chaitanya already mentioned this. He talked about cold chain and hot chain, and the one with the square brackets is cold chain and the rest are all hot chains. Now, if you look at the likelihood scores of the numbers in the square bracket, that is in the cold chain, and compare it with the likelihood scores of others in the same row, you will see that in the cold chain, the likelihood score is better. Right, so that's why it's sampling from the cold chain. The likelihood score there is much higher.
Yeah, and remember these are negative values. So the higher the number, the lower the value. Right? All right. So here we are with. So then, after running 50,000 generations, MrBayes gives you the option of running it further in case this average standard deviation of split frequencies has not converged, right? But here, now that since it's converged, we're just going to say continue with analysis. No, we don't want to continue this analysis any further because we are happy with what MrBayes has found for us, right? So we say no and we press enter. Does a whole bunch of things. Okay, now this is the interesting part. So if you look at where I'm pointing now, or where I'm highlighting, right, it tells you how the swaps have happened. So swap information for run 1 and swap information for run 2, right? So upper diagonal is proportion of successful state changes between chains, right? And lower diagonal is number of attempted state changes between chains. Yeah. So 1 is always your cold chain, right? So the number of successful state exchanges proportionally from 2 to 1 is 0.73, and the number of attempted is 8,281 state changes. So what it means is chain 2 has tried to swap with chain 1 8,281 times, and out of that, at a probability of 0.7 or 73% of the time, it has actually made the swap. Okay, so chain 4 has done it 0.36 times or 36% of the times, and so on and so forth. And then in the lower bottom, you see that there's this information, which is the chain information, right? It says my first chain is the cold chain, and this is that beta value that we showed in the presentation, right? So for the cold chain, the beta value is 1, which means the posterior probability does not get changed or does not melt. But for every subsequent chain, you see that the beta value is a fraction, which is lesser than 1, right? Which means these fractions are going to melt the posterior probability a little, so that these chains can traverse better. Okay, and you guys remember this hideous formula from that presentation, right? It's the same thing. Okay, so this is how the heat value or the beta value is calculated. Everyone clear? Everyone with me now? Cool. So now what MrBayes has done is it's given us a bunch of trees with the highest posterior probability, right? And what we need to do is we need to build a summary tree based on the best trees that have been sampled. Someone have a question? Okay. Now, how do we do that? So, I'm going to assume that the first 20% of my sampling was burn-in. Okay, which means I have to say that I have to ask MrBayes to discard the first 20% of the sampling and use only 80% of it. And I'm going to assume that that's where stationary distribution has happened. So how do I do that? There is a command for that. I can show you the command on the worksheet. So sum t burn-in equals x. Okay, so where x is the initial number of trees that have to be discarded. Okay, so what is 20% of? So we basically ran the chains for 50,000 generations, sampling every 1,000 generation, right? Which means each chain is giving us 50 trees. That's it, right? Now, what is 20% of 50? 10. So what I'll do is I'll say sum t burn-in equals I press enter, and MrBayes throws out the consensus tree from the sampling with the highest posterior probability, right? You can see the tree right here, and it also generates this tree and saves it in the same folder as your .next file or your MrBayes file. Yeah.
Chaitanya, can you go back through the last point again, where you are discarding the calculations like Y10? I just missed that.
Okay, I'll just take you back to the slide. So you remember this slide, right? Where you're saying
right.
Initially, the sampling is not stationary or it's not stabilized. And then after a certain point, it stabilizes, right? And you get stationary distribution, right? So we are assuming here that this burn-in is about 20% for our data set or for our run, right? And we're saying that we discard 20% of the initial trees. which is basically 10 trees out of 50.
Oh, this point I understood. The point is like like every 50,000 you selected 50,000, and per 50,000 it was reading just 1,000. So 50,000, 1,000 is 50, and 20 you generally discard 20%. So 20% of 50 is 10, right?
That's right.
Okay. Okay, done.
So you generally don't discard 20. We are just assuming that there is a burn-in of 20 because we ran it for very less number of generations. You won't get a clean graph like this on tracer. The tracer graph will be all over the place, right?
Okay.
So if you ran it for maybe 1 million generations, then we'll get a clean graph where we can actually decipher burn-in. So for that, for the sake of that, we are assuming that we're going to discard the
Chaitanya, sorry, can I just interject? Can you go back to that burn-in, that graph, that the presentation?
Yeah.
Okay, I just wanted to make sure everyone got this concept right, because this is very, very important in Bayesian analysis. So, forget about multiple chains, multiple runs and all that. Okay, let us just assume that we are running one chain. Okay, and we are using acceptance ratio. It has to be more than 1, and you get a better, if the acceptance ratio is more than 1, you get a better tree. So basically, in this graph, you can see on the y-axis, the likelihood score keeps going up because we keep getting better and better trees, right, with number of generations. So let's just assume we are running just one chain. Okay, and eventually what's going to happen, it's going to hit the peak, and it will keep sampling it at that peak, and it'll, it won't get a better tree, and basically likelihood score will saturate, right? And that is the stationary distribution. Now we don't want the early part of all the trees that we have sampled earlier when the likelihood score was going up, because it has not reached that stationary phase, right? So we have to actually discard those trees, and that's what is called burn-in. Now you have to look at your data and decide how many of your trees you want to discard. Okay, Chaitanya has decided 20%. He's confident that by then it has reached stationary phase, but you need to look at your data set, run it through a program called tracer, and see if it has, after how many generations it has actually reached stationary phase. And then you discard the first part of all the trees as burn-in, and you summarize the rest of the trees. Okay, I hope that clarifies it.
Yes.
Yeah, or there's another way of doing it a little more convoluted, because you have run only 50,000 generations. We can actually go back to the run. Which is summary statistics and all of that. So if you go back to the run, you can see at what stage of your run the average standard deviation of split frequencies gets to less than 0.01, right? But I think in our case, if you it's 0 here. Wow. Okay. So in our case, it was kind of good throughout. So just to be safe, let's discard the first 20% of the trees, and we build a summary tree, and we get the consensus trees, right? Cool. Now, let me show you how to open these trees using fig tree. So you go back to your folder from where you ran MrBayes, and you see that it is created a file called primates.next.con. See this file? So that is your consensus tree, and that's a tree file. Okay, I'm going to open this file using a program that Roy showed called fig tree. I say file, open, straight to the consensus tree over here. I say open. Right? So there, it gives me a tree. Now, is this tree rooted or unrooted?
Rooted. Rooted.
Rooted.
Okay. So whoever says this tree is rooted should basically send me a box of chocolates. Do you remember when we spoke about
It is
various
rooted.
tree building methods? We said
It is actually rooted. It's rooted using Gorilla.
okay. So is this rooted correctly?
No, we have to reroute.
No, not rooted properly. We know about the outgroup and we'll have to select it so that it can rearrange it again.
Yeah. So what we need to do is we need to select the if we know the outgroup. I'm hoping all of us will know our outgroups. We select the branch that leads to the outgroups. We select that branch. So once you click on the branch, it kind of highlights, and then you click on this on the top left. You see this reroute button, right? Click on reroute, and now your tree is properly rooted. Right? Now, let's get to the posterior probability values. Okay. So I go to
And Chaitanya, I'm sorry if I can just interject for a minute. This also drives home the point of routing. You see, the program a priori has no clue which is the outgroup. So probably what MrBayes has done, it's taken the first taxa in your alignment, and I think Gorilla is the first taxa in this alignment. I think so. And it has just said, okay, you have not told me what the root is, so I'm just going to use Gorilla as an outgroup and root the tree, and it spits out a tree. So this drives home a very important point that you have to be very careful how you, careful about what the program spit out, right? And make sure that you have given it all the information it needs. Sorry, Chaitanya, carry on.
yeah. So now let's figure out what the posterior probabilities for the branch lengths are. So we go to branch labels on your left and select branch labels and increase the font size so that everyone can see, right? Cool. Now it is at some branch times or some random thing. If you click this drop down, you will see probability, right? So click on probability. Now it gives you posterior probabilities for each of the branches, right? So that is that. So if you noticed when Roy built the Raxamel tree, the same drop down gave you bootstrap values, right? And here it gives you probability values or posterior probability values. So that is that, I guess, unless you guys have any questions.
Chaitanya,
Yeah.
posterior bootstrap was applied on, I think, nodes, or was it applied on branches?
It should be applied on branches.
Okay, so
Because
both.
that is what it's supposed.
Okay, so both these are bootstrap and posterior probability are applied on branches.
That's correct.
Okay, okay. And if you can just can you just show us a bit a snippet of how you can just take the thing into tracer and how it looks in tracer?
Sure. Okay. So let me open tracer.
Chaitanya, just hang on, just one thing here. Don't change the presentation. There's something wrong here, man. Because the branches leading to the terminal taxa also have posterior probability values. You see that?
Yeah, because the posterior probabilities are really for the branch lengths.
Branch lengths or the branch itself, right?
No, branch lengths. That's what the manual says.
Actually, it should be the branch leading to a particular relationship.
No.
So
So
if it is a terminal node, it is not really leading to a relationship.
No. So the deal is the posterior probability of the whole tree, right? That basically determines if the relationships are correct. And there is no change in the relationships. But these posterior probabilities on the branches denote branch length. So that's what I read in the MrBayes manual.
Chaitanya, I was actually, I don't know, I may be wrong, but I was applying these things on node level.
That is incorrect. That I think we are all in consensus that that is wrong, because there is no tree building method that can actually give you support values for a node. Because a node is really just an arbitrary point in the lineage where diversification has happened. So it's very difficult to quantify or enumerate support for that arbitrary point in the lineage, right? However, you can enumerate, you can give support to a branch that leads to two taxa, right? So
Okay.
branches are the only things that can be supported and not nodes.
Okay.
So I just want to sort of jump in and clarify. So in the past, it used to be called node support, which is incorrect because nodes actually represent speciation events. So it should be branch support. You know, basically two species, you know, branching together. So that's why, you know, it's actually branch support, not node support. But in the past, people have used the term node support.
Okay. Thank you. That was the confusion.
Yeah, that was correct. And even a lot of papers as we speak tell you that, you know, node support for this node is, you know, the bootstrap value is 95 or 98 or something like that. But that's actually wrong. It should be bootstrap value for the branch, not for the node.
Including papers that we have published.
Yeah, we are all guilty as charged, but you know, we all learn and improve ourselves, I guess.
So do we have a minimum
Yeah.
of posterior probability for a branch support?
Sorry?
Do we have a minimum value, such as, for example, for the bootstrap, we say 95%. Similarly, do we have the same minimum threshold for the posterior probability?
I think we'll.
So it has
it's very similar to a question that was asked yesterday. I think there are multiple connotations to it, so we'll get to this on the last tomorrow. Because a lower bootstrap support or a lower posterior probability can mean a lot of things. So let's get to that tomorrow.
Chaitanya, the bootstrap support or whatever posterior probability on branches, and for example, I'm just hypothetically asking, the values in branches and nodes, I think would they be very different or almost similar?
Well, I don't understand the question actually.
No. I think I understand it. Usually they are similar when you're comparing likelihood and Bayesian. Parsimony versus the likelihood-based methods, I don't know. So by usually they are similar. What I mean is that posterior probability of one in Bayesian, and when you look at the likelihood tree, usually it's 100% bootstrap support for that branch.
Okay.
Right. So normally we see that, but the posterior probabilities tend to be higher than bootstrap support. So sometimes, you know, you'll see 80% bootstrap support, but 0.95 posterior probability. Okay.
True.
So posterior probabilities often tend to be higher.
Yes. But I was just a little worried because if they are different, because I published few paper giving node values. So that is a problem.
Giving node values.
Yeah, so it is giving branch values, right? The values.
Yeah, yeah, yeah.
We've all done that. We've all done that.
We have all done that. Don't worry about it.
Yeah.
Another way of looking at it is just giving you support of a particular lineage leading to the bifurcation of two different species. It's not telling you like at what point or how much time it took for a couple of species to actually bifurcate into a couple of species. So it should actually be branch values rather than node values.
True. Thank you.
So basically, let's say you have a bootstrap value of 100 over on this branch. All it says is that these 5 taxa are monophyletic, right? It does not say that pan and homo are sister if this branch is 100, right? However, if this branch is 100 bootstrap, then you can infer that pan and homo are sisters because you can be sure they're monophyletic. You get my point?
Yes.
So if I have 100 here, I know that these 5 taxa are monophyletic, but I can't confirm to the relationships of these 5 taxa. I just know they all have a common ancestor at some point in time, right? The internal branches further in this clade, the bootstrap values on those actually determine if they are actually sisters or not, right? So that is how these values should be interpreted.
Chaitanya, any idea like in the same tree topology, why this BI values, posterior probability, is always higher than bootstrap values? Most likely, always I have seen for my case all the time.
Maybe because the sample size with MrBayes is more, right? You're sampling many more trees to come up with a posterior probability. But with RAXML, you're only doing 1,000 replicates, right?
Okay.
I think that is the answer.
Okay, so I'm not sure if it really answers the question, but remember that in your posterior distribution of trees, you might have very similar trees or the same kind of topology, but just with different branch lengths, right? So your relationships are still the same. Your branch lengths are going to be different. So therefore, your posterior probabilities are going to be very high. Whereas in Bootstrap, it is a completely different method that it is using. It is actually taking each character separately, putting it, and then it's resampling with replacement. So therefore, you might get completely different support values.
Okay.
Yeah, another way of looking at it is that in Bootstrap, each of those replicates is a different data set. Whereas here it's the same data set. And as Roy pointed out, we are sampling from a posterior probability distribution that has reached stationary phase. So all the trees there are pretty much the same. So, that brings about this discordance.
Okay.
Okay, so I think we're pretty much done here. Chaitanya, I think some people were saying, can you show how to use tracer? So can you just load the one of the P files on tracer and show it, the ESS?
Yeah, give me a second. Yeah, so this is what tracer looks like. So let me try and load one of the files that we. So I say go to file and say import trace file. Sorry. So let's pick one of the P files for run 1. There. So this is what tracer shows you. And when I go to marginal probability distribution, it gives me a curve like this. For log likelihood, right? Yeah.
Just go to trace.
Where is trace?
It's on a tab on the right. And you can reduce the burn-in to 0.
So I can modify the burn-in right here.
Yeah, you can double click on it.
To 0 and press enter, and it kind of shows me where stationary distribution happened, right? So it happened right here at this point.
No, I would say a little bit ahead, no? Where it is saturation has started. Yeah, right there.
Yeah. So I would say at about 5,000.
If you just go down. Yeah.
Okay, so if there are any questions, then if there are any questions, then please go ahead and unmute and ask, or put it in the chat box. Otherwise, I think we're pretty much done.
Yeah, I was actually hoping to finish before 9.
Okay. What I am interpreting for these probability values is it will tell us that for this particular branch, it is 0.95% probability that it is going to be of this length. So is it correct, or am I wrong here?
Yeah, and it also gives you, it also tells you that the probability of the existence of this branch, right? How sure are we that this branch exists, this branch that leads to species A and B?
Okay, so it's a cumulative of both of them.
It is not, it's actually 2 different values. I just checked. So there is support for the branch and there is support for branch length also.
Okay. Thank you.
And generally when we report in the paper, we report the support for the branch. Okay, any other questions?
So there, Jayalakshmi is asking, so do we have to look in tracer for both the runs?
Ideally, yes. You should look for both runs.
Okay. If there are any other questions, please unmute and ask.
It might not give the same values, Jayalakshmi, but let's say one run tells you 10%, the other one says 15%. It's better to choose 15%, right?
Yeah, another way of looking at it is so when Chaitanya presented the slides, so just think of them as independent robots on that large space. So you might end up in local optimum. So therefore, you have 2 different runs. So
sorry, Roy, just repeat what you said, the last sentence.
Praveen, I couldn't get you.
What was the last sentence?
No, I just want.
So I was just saying these are two independent runs. So think of it as these two different robots that Chaitanya was presenting in the slides across the tree space. So the idea is to try and get to the highest peak.
Yeah, but then we are also, because we are using standard deviation of split frequency, we are also assuming that they have converged to the same tree space.
Yeah. So
let's just make that.
Yeah. So by the way, I should also mention this. There is a possibility that both these, let's say these robots, these two different runs are two different robots. There is a possibility that both these robots might actually get stuck in local optimum. So it is, especially if you have a really large data set, it is probably better to actually run the same analysis twice or thrice, so that you're actually sure of your values.
So in that case, the standard deviation of split frequency for the two runs will be more than 0.02.
Yeah, because if the two chains have reached two different local optimas, they won't converge, and the average standard deviation will be greater than 0.01.
So if we get the average standard deviation as 0.01, should we run it for furthermore times?
You can be sure that it's converged, but just to be sure, overall, you can just run it again. See, the advantage with running it again is what happens is it will pick new seed values for all chains, right? So during the first run, if it ran from, let's say, for a certain chain, it ran from tree number 35. The second run, it will start from tree number 456, for example, right? And if the second run also gets you the same tree, you can be fairly sure that that's the best tree in your tree space.
Okay, just to make matters simple for people who are running Bayesian analysis, standard deviation of split frequency can be used to decide on how long to run your analysis, right? Is 1 million enough? Is 5 million generations enough? Or is 10 million generations enough? So basically, you use standard deviation of split frequency to sort of decide on that. So as soon as the standard deviation of split frequency drops below 0.02, the runs have converged. So you maybe run it for another 1 million and then you stop. Okay, so that is how long do you run it. And once you have finished the run, you then have to decide your burn-in. And to do that, you look into tracer and see where the two runs have saturated, and you decide your burn-in. Get rid of all the ones before the saturation point, and summarize the rest of the trees. Okay, so this is just like you can use it like a thumb rule, but I would advise that all of you please read the manual, because it's not as simple as this. The idea is that we have to ensure that the tree space has been sampled enough, because we cannot sample all the trees, but it has been sampled enough, and our confidence in the final result is high. So that's our main goal.
Okay, so if there are no further questions, then we can probably stop the session. I'm going to stop recording now.